It's useful to look at this graphically. So these are just some plots of the quantities that we had on the previous slide, right? So on the x-axis here, you have the cosine. So the cosine of A and B, right? So at this end, where the cosine is 1, you have documents that are almost identical to each other. And here you have documents that are very, very different from each other. And the red line is the probability that they will have the same. That a randomly picked bit will be the same for documents A and B. And what you'll see is, yes, sure enough. So if the documents are identical, you're guaranteed to have the same bit. So the probability is 1. And as the cosine decreases, as the documents get further and further away, you get a smaller and smaller probability for the bit being the same. Please note the y-axis is on log scale. Right? That's why it looks kind of funny. This line really goes to 0 at 0. It just the axis happens to be on log scale. All right. And the reason I'm doing that is I wanted to put some other curves for that. Right? So the red line is just for a single bit. And if you take something like a 10-bit hash code, the line drops down quite substantially. And the reason you want that is you want documents that are dissimilar to land in different buckets. And if you just take a single bit, that's not enough, right? So for a single bit, a cosine of 0.5, the documents are not duplicates of each other in any way, but quite a lot of them will end up having the same bit. Now, if you take it to a 10-bit hash code, you actually have a very small probability. If the cosine of the documents was 0.5, you have a probability of less than 0.0001 that a single bit, that a 10-bit hash code is the same for those two documents. But you still have this nice property that the higher the cosine, the closer they are in space, the higher the chance that the 10-bit hash code is going to be identical for the two documents. So that's the guaranteed part. Now this is just for one hash code. So what happens when you repeat the process L times? So here's the second graph. I still have the cosine on the x-axis. On the y-axis, I have the miss probability, that probability that two documents A and B will never ever collide. They will never end up in the same hash table bucket as a function of how far away from each other they are as a function of cosine. And what you see here is 3 different configurations. Right? So the red configuration is where I have 10 bits, so I'm taking these, the blue, the hash codes that correspond to the blue line in the first graph, and I'm repeating the process 10 times. Okay? So what does that give me? The axis, both scales are linear in this case, so what you see is what you get. So if the documents are very, very close to each other, say the cosine is 0.99, right? So you have 2 documents and there is 1 word that's different between them. For such a high cosine value, I am guaranteed to not miss near duplicates, right? So the probability of missing a near duplicate is almost 0. But as the documents start drifting apart, that changes, right? So, for example, if the cosine was 0.8, now a cosine of 0.8 is pretty high. To get a cosine of 0.8, the documents really have to be quite similar to each other. But with 10 tables, I will miss them almost surely, right? The probability of missing them is, what is it, 95%. So I'm only going to get about 5% of near duplicates if I define near duplicates as documents with a cosine of 0.8 or above. Okay? So I'm going to miss lots of stuff if I just use 10 tables. Okay. Now, what if I wanted to make sure that I find all the documents with a cosine of 0.8 as near duplicates? What if I wanted to make sure that they land in the same hash table bucket? Well, if I take 1,000 tables, I can achieve that. I take the same 10-bit hash codes, I take 1,000 tables. For a cosine of 0.8, I get almost 0% miss rate, so I'm going to find all the near duplicates with a cosine of within 0.8 cosine. I'm guaranteed that. But for documents that are smaller than 0.8, the miss probability grows very quickly. So, you know, for something like 0.4, which you wouldn't call a near duplicate, the miss rate is 100%. So that means they will not end up in the same buckets, which is good. That's what you want. Except what you want is you want to have a nice way to control this curve. And if you think about the expense, it's really quite expensive, right? So getting documents that are very close together is easy. I just need 10 tables. If I want 0.8, I'm going to have to use 1,000 tables, and that's a lot of tables. That's a lot of computation. Now I have another configuration here, right? I could get this 0% miss rate in a different way. I could just use 2-bit hash codes and 10 tables, and that would give me a curve like that. And I would have a miss rate of almost 0 for a cosine of 80%. And that's a lot more attractive, right? You're just using 10 tables here. So let me ask you a question. Why would you not want to use this configuration?
Because you get a lot of false positives.
Yes, you get a lot of false positives, right? That 0 miss rate is going to come at the very high false positive cost. What that means is I'm going to have lots of accidental matches in my buckets. Another quick way to see why this is not a good idea, think about the computational complexity. Remember, the computational complexity of LSH is n divided by 2 to the k. That's how many buckets you're cutting your space into. With this configuration, in how many buckets are you cutting the space? 4, right? 2 bits, 4 buckets. When you only have 4 buckets, this means that if you had 1 billion documents, each bucket is going to contain 250 million potential matches. So yes, you could use that and your miss rate would be quite low, but the computational cost of that would be horrendous. And the false positive rate, well, the false positive rate and the computational cost, they're actually locked in. They're pretty much the same thing in this case. Okay, so now what's the takeaway lesson here? The takeaway lesson is you have 2 parameters in the LSH, the number of bits and the number of tables. By setting these parameters carefully, you can get a system that is arbitrarily close to perfect, arbitrarily accurate, whatever your definition of a near duplicate is. So if your definition of a near duplicate is anything with a cosine of over 99%, that's enough. If your definition of near duplicate is anything with a cosine of 80%, that's enough. Okay? For any definition of a near duplicate, you can find the parameters k and l that will give you a nice miss rate and an acceptable false alarm rate. But some of these configurations will come with a very high computational cost. Right? Here you're talking about literally maintaining 1,000 hash tables. Now the hash tables aren't very big. Each one of them only has about 1,000 entries, but that's a lot of engineering to do. Okay? So it's a nice technique. You have to be careful about how you pick the K and the L. And another thing you should take away from this, it's easy to detect things that are very nearby. And as you broaden your definition of the nearest neighbor, as you broaden your definition of a near duplicate, it gets harder and harder to detect them.